So this is a very simple fire alarm. By default, the 477 segment display is going to display 10 seconds, and that's what we have gone with. There's a center button which is going to be used as a reset button, and every switch that you see at the bottom, 16 of those would correspond to, say, 16 different zones on a property or 16 different rooms, say, in a hotel. So if there's a fire alarm, which would be represented by a switch, there's a fire alarm right here. You see the corresponding LED, which is set as an alarm, lights up. And the timer then starts counting down. If I reset the alarm, then the light goes off, and also the timer goes back to 10 seconds. Now, if you have more than one alarm, say on a property, say room 0, room 4, and room 5, it'll still count down to 0, and it goes all the way count to the 0, and that's mean something has went wrong, and there were 10 seconds. Obviously you can set that time to whatever you like, but the thing is, if there's an alarm and if you're working on it, you can reset it by just pressing the button, and you keep on doing it until you fix the issue. Once it's resets, like the switch goes back to 0, and the alarm, which is the timer on the 7 segment display, goes back to 10 seconds. So it's a very basic and very good fire alarm system. Now let's see how the code is working. But before we start working on the code, let's try to understand. Let's have a quick look at the RTL schematic. Now looking at this schematic, the top right half of the RTL schematic is basically BCD to binary to BCD display. This is something that we have done in the past, and I'll leave the link and the thumbnail on the screen and also in the description. So that's pretty much what we have done in the past, and I would highly recommend you, before you get started, to watch that video. In a nutshell, you have this slow clock which is fed into a 2-bit counter, and this 2-bit counter will go from 0 to 3, and then once it reaches 3 it goes back to 0, so it'll just keep on doing it in loop. The reason we are doing that is so that we can display 4 different digits on a 7-segment display. Okay, so this decoder makes sure that one of the segment is lit up and the other ones are off, and it just keeps on refreshing the 7 segment display at a refresh rate of I believe it's around 25 milliseconds. Now we are only using 2 of those, but it just keeps refreshing all 4 7 segment display. You have this slow clock right here, 1 second. The output of that clock is fed into a module which is count down 10 seconds. So as you saw in the demo, by default the timer is set to 10 seconds, and it starts counting down. So every 1 second it goes down by 1. So 10, 9, 8, 7 goes all the way to 0. The alarm indicator, this indicator just makes sure whichever fire alarm is triggered is represented in the form of LED. So if there is a fire alarm or hazard in room number 1, LED 1 will be on. So if there are more than one fire alarm triggered at the same time, say room 1, 5, 7, 10, those LEDs will be light up as well. And then the main part, the finite state machine FSM, this was right here. This is basically responsible for making sure the countdown goes down by 1. That signal is triggered, only then it starts counting down. It also taking the inputs as room, and then we have the count here, which is basically the input. Okay, so that count is making sure that if initially the value is 10 seconds and it starts going down, you have the system clock over here, and then you have the reset button. Anytime reset button is pressed, this count is reset back to 10 seconds. So just remember that. So this is a very familiar RTL schematic from many of my videos will feature something very similar. So it's, you see, how you can make a couple of more modules, 3 modules, and you can put them together to make something exciting. And that's what we are doing. It's a very basic and a simple fire alarm system. Now let's look at the coding. So like I mentioned over here, from U0 all the way to U5, everything that you see over here, these 6 modules we have done in the past, so I'm not going to go into too much of detail, but I want to talk about the bottom 4 modules. I'm going to start off with countdown 10 seconds and what it is doing. So we have the system clock right here, and this is going to be a 1 second clock, okay, because the timer goes down by 1 every 1 second. Also, we have a reset button, we have the signal to trigger, and then we have the output, which is going to be the count. Okay, remember, when a signal is triggered, only then it counts. Okay, and this signal is triggered by when there is a fire alarm system. Okay, I'm also making a register here. It's for the count, and I'm naming it as current count, initially set to 0. When the positive edge of the clock arrives, if the reset button is set, then the count goes to 10. Remember, it's counting downwards, so it's going to display 10 seconds. Else, if signal is 0 0, this is sort of like initially, that's how the condition is, kind of a reset, so make sure the current count is 10. Else, if signal is 1, and current count is not equal to 0, that means if the alarm is on, if one of the alarm in the room is on, triggered, and the countdown has not reached 0, it will keep on decrementing. The current count will keep on decrementing by 1. Else, current count gets current count. So it's pretty simple. And then finally, saying assign count equals to current count, because we want the timer to be displayed on the 7-segment counter. So that's your countdown, 10-second countdown timer. Okay, we also, obviously we are counting it down by 1 second, so we need a slow clock with 1 second. So it takes in 100 Hertz system clock from the Basys 3 board, and it outputs 1 second clock. So this is going to be a 1 second clock right here. For that, we need to create a register. I'm going to name the period count equals to 0. This register can reach up to maximum value of, I don't know what that number is, but surely this number, if you do the exponential power for base 2 to the power 27, because it's a 27-bit size register, that should give you, to the power 27 should give you a number greater than that, and that's what you need. Okay, so make sure this number is 26 and this number is 0. That gives you 27 bits. Okay, all right. And why we are going to for this number? Because the Basys 3 has a system clock of 100 megahertz, so 100 million clock cycles right there. So when the positive edge of the clock arrive, again this is a system clock, we look for the period count, whether the period count has reached this number. This number is 100 million minus 1. So if the count has not reached, then it should just keep on incrementing by 1. And the clock at that time, we are setting it to 0. Initially the clock is 0. Else, if the period count has reached 99 million, that is when the period count reset itself, goes to 0, and the clock then inverts. Initially was 0, now it goes to 1, and now it's has completed it 1 complete clock cycle, and this keeps on happening in a loop. So basically you have been able to generate a 1 second clock. That is what we need for this countdown timer. Okay, next is the alarm indicator. This is the most easiest one. So input are the alarms, so these are all the rooms or zones on the property, and the output is the LED. This is the corresponding alarm light. Okay, and we just simply assign every LED to its room. Okay, so if room 1 has a fire alarm on or triggered, LED 1 is going to light up, and similarly if there's a fire alarm in room number 15, LED 15 is going to light up. This is pretty much what it's doing. Fairly simple. Let's move on to the next one. Now You might think like why do I need 8 bits for the count, because we are only going from 10 to 0, like 10 seconds, 9, 8, 7, 6. So 4 bits should have been enough, because 4 bits go from 0 to 15. And like I said, a lot of it is from the past videos. In the past videos, and I had the 8-bit, so I just went with that. It should not matter. But in case if you need to change that, you should be able to do that pretty easily. So again, this is the finite state machine. Again, this is the clock, reset button, room, this is the count, and this is the signal. Okay, so it counts down only when the signal is triggered. I have created 4 constant right here. I might not necessarily going to use all of them, but like I said, a lot of it is from the previous project file, so I'm just keeping it in there. You can use them for other features if you wish to add into this video. I also have line number 15, 16. I got the current state and the next state. Both are 2 bits initially set to 0. And I also have 2 more register, line 20 and 21. Initially, all the LEDs are set to 0, and initially the signal, I'm setting it value to 0 as well. When the positive edge of the clock arrives, if the reset button is pressed, then the current state basically gets 0, 0. This is the reset state, folks. This is our initial state, if you want to call it. So else the current state will move to the next state. Now, this is the next state combination logic right here. Again, when always at current state, so we are looking at the current state, and we are looking at all the inputs, which are basically the room. Now for current state, we got 4 different combinations, and like I said, initial, this S00, this case is basically the initial state. So if any of the room alarm is triggered equals to 1, then the next state, it goes from S00 to S01, else it stays S00. If you are S01 state, that means one of the alarm has triggered, then it waits for the count to go to 0. And if that's the case, and also if all of the rooms, if any of the room is equals to high, and if those conditions are met, then the next state is going to be S01, because you still have the alarm on, so it will stay there. Else the next state is going to be S00. If no alarm is triggered, then it goes back to its initial state, which is going to be 00. We also have this state right here, line number 43. If any of the, which I just basically mentioned, right? If the alarm is not triggered, it goes to 0, then next state is 00, which is the initial state. Else next state is going to be S01. We have another state, S10. Look what's happening over here. So if all the inputs that you have, they are equal to 0, then the next state is going to be the S11. Else next state basically stays at S10. And really I could have just avoided these 2 states, but because I had it declared over here, I'm just using them. Okay, so if you wish, you can change them around. And the S11 is finally the reset state. If that is the case, then the next state is going to be S00. Next state, otherwise just basically go to the S10, okay, followed by N case, and then finally the N. Now this part of the code is basically what it's doing. For set signal, we declared it as a 2-bit, so I got 4 cases here, 0, 1, 0, 1, 0, 1, 1. In the 00, it's basically no alarm is triggered, so it does not start counting downward. There, now the trigger, it has triggered. S10, all the alarms are now triggered back to reset value, and S11 is the reset condition when the reset button is pressed. When that is the case, the signal should be 2 bar B11. And for all these situation, we have we have looked at what's happening under different cases, followed by n, and finally don't forget to have your signal set signal value stored in a variable which we declared as a signal. And finally, if you look at your top module over here, again, you got your clock, system clock, you got 15 rooms as an inputs, you got reset, 4 enablers, 7 segment display, and then 15 alarms. Initially, for all the 7 segment, we are setting it to value of 0, so all 4 segments are enabled. This is the 100 Hertz clock for setting up a refresh rate for 7 segment display. This is a 1 second clock declared as a wire. This is a signal to trigger the countdown. You have the wires for the mux, counter out, ones, tens, and hundreds, and count. This is basically this part of the circuit over here. Everything. Remember, when one module is connected, the output of one connected to the input of the other, those need to be declared as wires. So over here, if you look at the U0 module, 100, ones, and tens, these need to be declared as wires, and that's what it is. Similarly, we have a wire counter out. This counter out is basically this right here, U3, the output of the U3. So if you have a good understanding of your RTL schematic, you can better understand the code. So what we're looking at right now is the top module. This is again the binary to BCD. Again, it should be on your screen, so please watch that video. And finally, the last 4 modules, this is what the fire alarm system is. This is what we have added to what was already there in the other project. So countdown here, this is our identifier U6, and new clock out, reset, signal, and count. I just want you to remind you one more time, folks, this sequence does matter, and it should match with how you have in your source file. So if I go to countdown, I should have my new clock out first. Countdown here you go. Here's my clock, then my reset, then my signal, and then my count. So it should follow the same sequence over here as well. You got your clock, you got your reset, you got your signal, then you got your count. Similarly, same sequence should be followed over here as well. This is a slow clock for 1 second, you got the system clock, and then the new clock out is the 1 second clock, which I also mentioned over here as well. Okay, and then finally you do it for FSM, again, clock, reset, alarm, count, signal, and module, and that's pretty much it. If you go to the constant file, we need 15 switches. You have the clock right here, you have the center button for the reset, you get the 7 segment, and right below that there are the 4 enablers. And then you have the 16 switches as as rooms, and you got 16 LEDs, alarms, and alarm indicator. And all you need to do, save everything, click on run implementation, generate a bitstream file, and upload your program onto your FPGA board, and that's pretty much it. It's a very basic and a simple project, an intermediate level project that you could do for your any engineering course, FPGA engineering course. I hope you enjoyed this video. I went through quick, but a lot of stuff was something repetitive. We have done it in the past, so I will leave the link of those videos in the description. Enjoy your rest of the day. Till next time, bye bye.